Grey Cantoma. On this video I'm going to be showing you how to design your beam using RCD 2000. Okay. Now let me briefly explain. Now on this, as you can see, this shape is actually L shape, right? Now that makes beam 1 to be an L beam. Okay. This shape is actually a T shape. You can see the shape. That makes beam 2 a T beam. Okay. This shape is a T shape. That makes beam 3, which is this, a T beam. Okay. Now we are designing this particular beams. As you can see, this beam now is 230 by 450. We want to design it as 230 by 450. Okay. Now on this video I'm only going to design beam 1, beam 2 and beam 3. I actually want to make it as brief as possible. Okay, I want to make this video actually brief. Now if that is correct, now these values that you see here are gotten from our slab. Okay, these are values which we got from our slab. Okay, let me briefly show you. When you go to your RCD, that's your slab result. Okay, you know the other time we saved it as proposed. So you open, as you can see on panel 1, look at the short span. This is what we got, equivalent UDL on beam 13.43. so you come here on panel 1, the short span 13.43. Okay. This is the other part of this panel 1, which is also a short span, which is 13.43. You can see both left and right, or you can see up and down. Okay. When you go to panel 3, or let's see panel 2, panel 2 is actually a one-way slab. So you can see left shear on beam / wall 11.73 kilonewton per meter. Okay. Since it's a simply supported, now your loadings are only going to be concentrated on the short span. Okay, look at this is what I'm trying to say. Now look at it on panel 2. Okay, this is it. As you can see, this is your short span, right? Now this is the beam. This beam here, beam 3 and beam 4 are the beams that are actually carrying this load of this slab in panel 2. Okay, this particular beam is only carrying itself with this beam, that's beam 7 and beam 5. Okay, along this span are only carrying their self weight, which is 3.01. I'm coming to that. I will explain where we got 3.01 and 2.88 from. Okay, now this is what we got, which is 11.73. okay, from our slab. 11.73. okay, both left and right. That's, we assume here to be left, here is right. 11.73. now okay, when you go to panel 3, okay, let's go to panel 3. Panel 3, the same thing, 13.43 on short span. What do we have on 17.608 on long span? Okay, on panel 3, short span 13.43, long span 17.61. Okay, same thing with our panel 1. So that means panel 1 and panel 3 are actually identical. So when you go to panel 4, you have 9.10 kilonewton per meter. Okay, both on left and right. Like I explained the other time, since it's a one-way slab, it's simply supported. Now it is only carried by this beam, which is beam 1 and beam 2. Okay, this particular panel 4 is carried by beam 1 and beam 2 on this span. Okay, so I'm only going to design our beam 1, beam 2 and beam 3. Now we said beam 1 is an L beam, beam 2 is a T beam. Now this beam, as you can see, is not resting on a column direct, it's on a beam that is acting as a point load on that particular beam. Okay, I may not be able to cover everything on this particular video, but I'll try my possible best to show you the basic things that you need. Okay, now this little calculation, I believe you know where it's coming from. 0.15, which is the thickness of your slab, multiplied by the density of concrete, your finishes, we say, let's say 1.2. okay, these are the finishes, partition allowance that we want to use in this design. Now take note that is not always a constant value. I will always refer you back to reinforced concrete design book by Victor O. Oyenuga. He's a Nigerian, or you can get this book by Mosley and Bongi. Okay, these books will actually help you and give you a better insight of what we are doing today. Okay, effective span effective depth ratio for beam and slab. Okay, for simply supported is 20, for cantilever is 7, for continuous is 26, for two-way. Now for two-way, anytime you have at least one edge that is discontinuous, you use 23. Okay, we will come back to that where you will have a better understanding. Now beam load. Okay, for L beam, when you have, for example, an L beam of 230 by 450, okay, this is the self weight of concrete plus the self weight of plaster. Now this is the value you get whenever you have an L beam of 230 by 450. This is the value you should use. Okay, that means whenever this dimension or whenever the thickness of this beam actually changes or it reduces, now you cannot use 3.01. so what I'm trying to explain right now is this, that this value is not always a constant. It's not a constant. Okay, it's not a constant, but you only use it for a 230 by 450 beam. That means when this beam changes to 230 by 600, for example, this is not the value you use, but this is just like a formula for it. Okay, since beam that we normally use, that is most common in most of our buildings, is mostly 230 by 450. Okay, so it's 3.01 for an L beam. So you can see the calculation is very simple. Plaster, concrete, self weight. Okay, for your plaster 0.3, that's the bottom depth of that beam, and then the width of the beam, the density of the concrete times the factor of safety when you come to plaster. Now it's very simple. Okay, the depth, bottom depth of that beam, okay, the width of the beam, and then the overall depth of that beam is 450. Okay, I don't want to go deep into explaining what this is, but it's very simple and self-explanatory. Okay, you can just go on your own and you understand everything that is actually going on here. Now when you come to your T-beam, the same thing, just like as I explained in that of your L-beam. Okay, the same thing. Now when you have 230 by 450 beam, you always use the value 2.88. okay, that means when it changes, definitely this value 2.88 will change. okay, when you have 230 by 650 or by 600 rather beam, now this value changes. But this is just a simple way to get whatever value you want to use here. okay, it's just like the self weight of that particular beam. Now, breadth of flange. okay, we have breadth of flange for L beam, we have breadth of flange for T beam. okay, the breadth of flange for an L beam is always 0.0 times the maximum span plus your breadth of web. Now 0.07 is actually gotten from a small formula. I will always refer you back to Victor Yenuga simplified reinforced concrete design book by Victor Yenuga. okay, you can get that book for yourself. But down below the description of this video, I'm going to drop a link where you can contact me either in any of those social media platforms, or you can chat me up on WhatsApp, and I will guide you on how to get this particular material. okay, the BF of T-beam is 0.14 times the maximum span, okay, plus BW. okay, now if that is that, let's go back to our design. okay, to design beam 1 now, we'll go to our RCD 2000. okay, click on beam, you drag, you drop on your drop box. okay, okay, your T, you press enter, your F, you press enter, your file output. okay, let's say beam design. okay, no password, job reference, job reference is just your job number. okay, since this is beam, we have done our slab. okay, this is beam, let's say 2, engineer G.K March. Number of beams. Now, like I said, I just want to design only 3 beams. But now, if you check on this particular GE, we have 8 beams. okay, we have 8 beams. So I'm only going to design 3 beams, which is 1, 2, 3. So I'm going to input 3. So 3, concrete 20. okay, steel 410, steel rope 250. okay, your steel rope is your mile steel. okay, 3. okay, enter. okay, enter beam ID. okay, beam 1. I'm going to design beam 1 now. Enter number of supports. Now on beam 1, which is this is beam 1. okay, we have 1, 2, 3, 4. Now we have 4 supports. Now we have 1, 2, 3 span, 3 span, 4 supports. I hope you understand that. Now we have 3 span, 4 supports. So I'm going to type enter number of supports. We have 4 supports, we have 3 span. You press enter. Enter support grid number. okay, now beam 1, right? okay, this is our beam 1. 1, 2, 3, 4. That's our grid number. 1, 2, 3, 4. So 1, double space 2, double space 3, double space 4. You enter. Now what is the width of that beam? Now the breadth, okay, is 230. Now what is the BF of beam 1? Remember we said beam 1 is an L beam. Okay, since it's an L beam, what is the BF? We have done that calculation. For beam 1, okay, it's an L beam, which is 3.01. 3.01. I hope you understand. Sorry, it's not 3.01. BF, okay, BF L beam, BF for L beam is 498, okay, 0.07 times maximum span. Now let's come back to this. What is the maximum span? Okay, all the spans are actually equal, so our maximum span is 3830. Now in a case whereby this span is not equal, maybe one is 1000, the other one is 2000, the other one is 3830. Now the highest will be 3830, which is what we are going to use. So it's going to be 0.07 times 3830. Now plus your breadth of web, which is 230. Now when you do this little calculation, you get your value as 498. Okay, 498. Now what is the depth of that beam? Remember we said it's 230 by 450 beam 1 to design. Okay, what is the HF? That's the height of flange. Height of flange is part of that beam that enters into the slab. Okay, that's the thickness of your slab, which is 150 HF. Now enter end support type, loads, moments, if any. Now what this means is this: on this end support, now look at, we have, this is one end, this is the second end. Now on this end, now you check on your GA, there is no load that is actually acting on this particular support. Okay, there is no load aside. What that means is when there is maybe like a point load you get that is acting on that support directly. Now there is no load acting on this end support directly. There is no load that is acting on this end support directly, so it's going to be 0. Now when there is no load, that means there will be no moment, because our moment is force times perpendicular distance, and we know load is in kilonewton, right? Now our force is kilonewton, that means force times perpendicular distance. So when there is no load, there's actually no moment. Okay, so I know this place is actually somehow confusing, but I don't know, I just pray God will help you to understand. Okay, there is no load that is actually acting on this column directly. Okay, on this support, rather on this support. Okay, like a pointed load. Okay, there is no load, so it's going to be 0 space 0 space 0. Now enter end support type. Okay, this end support type, we have two different kinds of support. Now when you have a fixed support, okay, or a built-in support, okay, is actually going to be 1. Now when you have a fixed when you have a hinge support, or mostly when you have a hinge support or a pin, is actually going to be 0. Okay, so now this first 000 is for the first support, the second 000 is for the last support. Okay, now the first 0 is for which type of support. Is it a fixed support? Is it a hinge support? Is it a roller? Okay. In the manual, you are going to see it captures everything. Okay, the manual actually captures this. So in the manual, you'll be able to have a better understanding of what I am trying to explain right now. Now enter member serial number, span and load. Now this beam one, okay, this is the first member, this is second member, this is the third member. Now on member one, we are asked to enter the serial number. We are going to say 1. Enter the span is 3830. Now enter the load. Now we have load which we got from our slab. Okay, we will sum that load from the slab plus its self weight. It will give us 16.44. Now we will type 16.44. Okay, now there are other 3 different loadings. Okay, we can have a triangular load, we can have a trapezoidal load, we can have a point load. Now we don't have a triangular load on this particular support. We don't have a trapezoidal load on this support. So if there is no trapezoidal load, there will definitely not be a trapezoidal height. Okay, so it's going to be 0. Then the last one is going to be 0. There is no point load acting on this beam. Now beam 1 is actually different from, okay, look at this beam 8 now. When you come to beam 8, there will definitely be a point load because this particular beam 2 is actually resting on beam 8 direct. Now it's going to act as a point load on beam 8, but on beam 1 there is no point load, so it's going to be 0. So our serial number, the span, the load, the uniformly distributed load, which is 16.44. Now then the triangular load, then the trapezoidal load, trapezoidal height, then point load 0. Now on span 2 is actually the same thing as span 1. Okay, the loading, it spreads to span 2. Okay, now it is uniformly distributed up to span 2. Now it is going to be serial number 2 3830. We have 16.44. We have 0, 0, 0, 0. So this, okay, yes, correct. Okay, then we'll now go to span 3. We press, what is the span, which is the same thing, 3830. 3830. The load is 12.1. Okay, 0, 0, 0, 0. Now we are done with beam 1. Okay, now let's go to beam 2. Beam 2. Now enter number of support members. Now this is your beam 2. Okay, this is beam 2. On beam 2 we have 2 supports, we have 1 member. Now you know the beam that is resting on is acting as a support to it. Okay, it's actually resting on beam 8 and beam 7. Okay, so it has 2 supports and 1 member. Now enter support grid number. Now on this beam 2, we have, is resting on, is on grid 3 and grid 4. Right, now we type 3 space 4. Now enter beam width, is a 230 beam. breadth of flange. Our breadth of flange, you know, this is a T-beam. Okay, you go to that little calculation we did the other time. Okay, it is a T-beam, which is 0.14 times the maximum span plus 230. Okay, another thing you should take note of is when you are dealing with BF, you know, the calculation for L beam when it is a continuous beam and calculation of T beam when it is continuous is different from when you are dealing with a T beam when it is simply supported, or an L beam when it is simply supported. But in this particular video, I am not going to go deep into that, okay, because I'm trying to make it as brief as possible. That is why I will advise you to get the Reinforced Concrete Design book by Victor Oyenoga, and you get the manual of RCD 2000. You can get it from me. Yes, I will refer you. Go down the description of this video. I'm going to drop a link on my social media platforms where you can contact me directly and get yours ASAP. Okay, if you are enjoying this video, why not give it a thumbs up? Okay, subscribe to this YouTube channel. It's actually free. You see a red button down below. There is a bell. Click on that bell icon. You get a notification whenever I drop a video. I drop videos on daily basis, sometimes on weekly basis. Okay, so as to encourage people who are trying to understand designs better. Okay, and again, the design of this slab is actually, we've done the design of this slab already. You can go to that YouTube channel, which you are still going to get down below the description of this video. Okay, now is a T-beam 230 by 450, so we are going to use 766, okay, for the sake of this class. Okay, the depth 450. Now HF, which is 150. Hope we understand this. Okay, press enter. Now enter any support type. Okay, on that support, is there any load on it? Is it a fix? Is it built in? Okay, is it hinge? Okay, that will determine what value you should use. Like I said from the beginning, if it is built in or fixed, it is 1. If it is a hinge or a pin, it's actually 0. Okay, so now the load, when there is no load, on that support. Let's come back to the drawing. Is there any load acting on this particular support area? Now there is no load acting on it directly outside its self weight. Okay, outside its self weight. Okay, so we are going to put 0, 0, 0 now on the first support. Then the last support is also 0, 0, 0. Press your enter. Now enter serial number. Let's say 1. What is the span? 3830. Now what is the load that is acting on this particular support, on this particular beam 2? Now is 9.1 plus 301, okay, which is 12.1. I believe you understand where we got this value from, which is 12.1. Now triangular load 0, trapezoidal load 0, trapezoidal height 0. Point load, there is no point load acting on that particular beam, is 0. Now we have designed our beam 2. Now to design beam 3, we say BM3. Okay, enter number of supports of beam 3. This is beam 3. Look at it here. We have 1, 2, 3 supports. Okay, now how many span? 1, 2 span. Okay, we have 2 span. So we have 3 support, 2 span. Okay, enter support grid number. Okay, support grid number. Now beam 3 falls under grid 1, 2, 3. Okay, so to type 1 space space 2 space space 3, you press enter. Enter beam width, it is a 230 beam. Breadth of flange. Now we said beam 3 is actually a T beam, right? Beam 3 is a T beam. Okay, now go back here. For our T beam, you know it is 0.14 times the maximum span, but the span is actually equal, so the maximum is definitely going to be 3830. Now, like I said earlier on, the span might vary. You know, you may have different sizes of span. Okay, they may not be the same. So in that case, you pick the highest. Okay, 0.14 times the maximum span plus your breadth of flange, which is 230. So our value is what? 766 for T beam. Okay, 766. Then your depth is what? 450. Then your height of flange is 150. Then you enter. Now enter end support type. Okay, 000. I believe you understand where we got this from. Okay, it's actually, we said there is no load on it, so there will definitely be no moment. Okay, and then the type of support, is it a fix, it is build, or the rest. Now on both first support and the last support. Now enter beam serial number, you know, for the member. Now, you know, this is the first member, this is the second member. Now this first member, okay, what is the serial number? We say 1. What is the span? 3830. Now what is the load that is acting on that particular member? That is this member. What is the load acting here on this place? Okay, when you sum 13.43 plus 288 plus 11.73, now you will notice that this beam here, which is beam 3, you notice is actually carrying a load from this panel and is carrying load from this panel. That means the internal beams carry more load than external beam. You can see it's carrying from both sides, from panel 1 and from panel 2, from panel 3 and from panel 2. Okay, now that of panel 2 is 11.73. when you sum everything, it gives you 28.1. so you type in 28.1. okay, that is the load acting on that particular span. Okay, triangular load 0, trapezoidal load 0, trapezoidal height 0, point load is 0. Now span 2 is actually the same with span 1, as you can see here, it's the same. Okay, so it's 3830. That means it is uniformly distributed all through. Okay, so we are done with our beam design. Okay, we are done with our beam design. If you are enjoying what you are seeing, why not give it a thumbs up? Okay, subscribe to this YouTube channel. It's actually free, you don't pay a dime. Okay, we have some other videos: design of staircase, design of your columns, design of your base, design of your slab, okay, using RCD 2000, and then designs using Prota structure, using Orion, using AutoCAD. Okay, all in our YouTube channel. Okay, you can just visit that YouTube channel, keep yourself busy, learn more. Okay, down below the description of this video, I'm going to drop that link. You can visit that channel and then engage yourself. Okay, now what we'll do next is to check our result. Okay, go to RCD 2000. we named that what did we name it as? I think we just designed, yes, we say beam design, right? Which is this. Notepad. So let's design it. Okay, you can see your bottom bar, your top bars. Okay, all 3y16, 3y16 for beam 1. Okay, for beam 2, 3y16, 3y16, bottom and top, all 3y16. Okay, let's see, our links are going to be 300 y10, 300 spacing center to center. Okay, go to beam 3, the same thing. Okay, if you have gotten up to this stage, congratulations. Okay, because beam is actually one of the most complicated. Okay, you can understand beam very well. I think every other aspect of the structural members is actually going to be a walkover for you. Okay, now after all these designs, we are going to use our values or our results to actually come up with a detailed drawing. Like, you know, you don't design with AutoCAD. Okay, please, I know many people are actually getting it wrong. Okay, you don't design with AutoCAD, you only detail with AutoCAD. Now whatever result which we've gotten from our calculations, like you can see this one we got here, you know, it's telling you your top, which is 3y16, bottom 3y16. When you come to your design of your beams, that is where you begin to include those values. Okay, now if that is correct, we do designs as a consultancy. You can bring us in when you have a design. We can design for you for at a cheaper price, at a very cheap price. We'll design for you. We do structural designs, we do architectural designs, we do electrical and mechanical drawings. Okay, we do all these drawings. For your structural design, stamp and seal from a Korean registered engineer. We give you your bar bending schedule and then the volume of concrete design. Okay, my name still remains Abel Grey Kantuma, and then